So today we are going to talk about battery pack design with cell balancing and thermal management with Simulink. So I'm going to introduce you the agenda of today's webinar. So we will start the presentation with some insights that we see in the electrification and the industries around electrification. And then we are going to jump to the technical topics. So Simscape battery introduction, and I will walk you through the battery pack design and battery management system design with Simscape battery. And in the end, we are going to take a look at how you can implement battery packs in electric vehicle models. So let's just start with the trends that we see in the electrifications. So what we experience in various industries that all of the industries are turning to more and more electrification in their developments. So the electrification targets show an increase in battery demand. On the right of this slide, you can see the battery demand forecast of the automotive industry only. So we can see that by 2030, there will be a demand of 1,000 gigawatt hours to be stored in batteries only by the automotive industry. So it doesn't include aerodef or grid applications. So this shows a huge increase in storage systems in the next couple of years. And according to industry leaders in Europe, we not only see development, but we also see challenges that we need to focus on if we want to reach our success criteria in the electrification. And speaking of the success criteria, we have defined and we see three main success criteria that we need to take into consideration. So what we need to do is we need to maximize the capacity of our batteries, and we have to make sure that the energy density of our battery systems is increasing by time. And we don't only need to have big battery capacities, but we need to ensure the safety goals of the new technologies. So implementing a reliable and safe battery management systems is key to the success of battery management. And obviously we are on the market here. So if you are designing or developing a battery system, it is key to get on the market as soon as you can. So if you are reducing your time to market, then you are having an advantage over your competition. And for these, good models and virtual testing is crucial. So with those three success criteria in focus, MathWorks decided to bring a solution for this, and it introduced Simscape Battery as a toolbox for you that you have available in Simulink, and it provides a framework for you that is assembled specific to create a bridge between battery cells and the system that you want your batteries to implement in. So what you are going to start with, you are always starting with a cell design. Then you are moving forward. Then you organize your cells into a pack design, and you start to develop your algorithms, battery management system algorithms, and thermal management algorithms around your battery cell and battery packs. And with Simscape Battery, you can also reach system implementation regardless on your industry type. So it can be also an electric vehicle, kind of an electric car. It can be a grid application, or it can be also an aerospace system that you want to implement your battery packs into. Before we dig deeper in Simscape Battery, I would like to have an intervention because we get questions frequently on Simscape Battery and finite element method simulation. So I would like to highlight what are the main differences between Simscape Battery and a finite element method simulation like COMSOL, for example. So with Simscape Battery, you can go cell and above level details, where you can include control system design, and you can get information of your cell and of your system, for example. While having a COMSOL simulation, a finite element model simulation, you can also capture below details below cell level. So you can see that on the left, we have a scope where we see the state of charge of one cell, for example, that we can reach with a Simscape Battery. But if we are interested how the temperatures inside the cell look like, then COMSOL simulation can offer us a solution. Also, Simscape Battery is a system simulation, so it offers fast simulation times. And if we want to catch those details with console, then we need to moderate the simulation time. And yeah, so if you wanted to go and choose between Simscape Battery and console, then with Simscape Battery, you have an ideal choice for cell to system level modeling. And with console, you have ideal option for capturing local effects. Today, we are going to focus on Simscape Battery, but we are also having sessions on console. So if you would like to get more insights on console, then my colleague Arpad Forberger will deliver webinars on it. So check our websites and stay tuned. So speaking of and continuing with Simscape Battery, you can go from cell level to pack level with Simscape Battery in the matter of a few steps. And you can see a chart of the workflow itself. So you will start with a cell and you will reach to a pack, but you have some initial steps in the meantime that you have to take. So you will go from a cell to a parallel assembly. So you start to assemble your cells and you will create modules using the parallel assemblies. And you will scale up the modules to module assemblies and battery packs. And during those steps, you can run simulations and define and visualize the simulation strategy that you want to use. So if you need a really detailed simulation, then you can go with the detailed one where each cell represents one element in your model. Or if you need and if you want to do more high fidelity models, then you can group cells together. So your grouped cells will represent one element in your model, or you can even simplify your models to a lumped model, and one cell, one whole pack can be simplified to one element in your model. So this is what Simscape Battery offers you, and you can use it for the main workflow teams, for example. Obviously, you can use it for battery pack design, but you can also implement thermal management system design and battery management system design to your around your battery pack design workflow. So those are the three main topics that are supported in the simulation domain. And also, Simscape Battery offers support for deployment to real-time machines and hardware-in-the-loop simulations. So you have a flexibility there if you want to deploy and test your models, let it be rapid control prototyping or hardware in the loop. Simscape Battery supports that. And if you want to work with Simscape Battery, then you have two main options. You can either choose to go with the battery builder application, or you can use the Simscape Battery API if you prefer coding over user interfaces. So with the battery pack builder app, you can inspect the hierarchy and create components and visualize components of your design. You can create new cells, new modules, and pack objects, for example. You can also import existing battery objects to the battery builder application. And what is the most important, that you can create Simscape battery models from your objects that you have built in the battery builder application. On the other hand, with the API, you can create automated scripts to create and generate cells, battery modules, or battery packs. And you can also obtain and modify object parameters programmatically. So it gives you high flexibility and high level of automation. And of course, you can generate Simscape battery models using scripts there. So based on your choice, you can decide which one you prefer, and you can decide which one you would like to implement in your workflow. But speaking of a specific battery pack and specific objectives of this webinar, we are going to take a look at how you can create an 18650 battery cell object, and we will use this 18650 battery cell to build a 5PCX6S battery module, and we will scale up our module to pack level. And here we will create two variants of the model. We will create one detailed battery pack, and we will create one simplified or lumped battery pack. And also we will implement the battery to the electric vehicle reference application, which is an automotive example, but this example and implementation is not specific, not restricted to automotive applications. So you can also use it for aerodef or grid level applications, for example. So let's take a look at the parameters that we will use for the cell, module, and our pack. For the cell geometry, we are going to use an 18650 battery. So this gives the geometry of our battery. We will have an 80 millimeter diameter battery with a height of 65 millimeter, and we will have a cylindrical shape. We will define a capacity for our battery to have a 2.8 ampere hours, and the thermal modeling will be enabled for the simulations because we want to catch the thermal effects of the battery pack. As for the module, we will have a layout as follows. So we will have 5 cells in parallel, and we will have 6 cells in series. So for those building blocks, we will use parallel assemblies and the module block. And again, we are modeling thermal effects, so we will enable the bottom cooling. We will create a bottom cooling plate, and we will enable the battery cooling. And going further to the pack parameters, we will have a layout where we have 30 cells in parallel and 96 cells in series. And we will create the 2 variants, the detailed model and the lump model. And we will try to reach the energy of 80 kilowatt hours to be stored in the battery pack. So now that the parameters are clear, let's jump into MATLAB and let's take a look at how you can do the design of such a system. So once you open up MATLAB, you have 2 options to open up the battery builder application. You can go to the apps tab and open the battery builder from Simscape, or you can also open it from the command window using the battery builder command. I have already opened up the battery builder, so I will just open it from the opened windows. And once you open up the battery builder, you will find this UI that you can see on my screen. So here you can see in this tab, we can create new cells, new parallel assemblies and modules. And then our cells and our objects that we create can be visualized in the middle. And we can define the properties of the batteries on the right pane. So I have parameterized the properties in advance. So let's take a look at how you can do that later, and if you decide to do it on your own. So under the geometry tab, we can define the radius and the height of the battery. So again, we are modeling an 18650. So it will have 9 millimeter in radius and 65 millimeters in height. I have defined the values in meters, and I have chosen the cylindrical battery geometry for this. Under the cell properties, we can set the capacity and the energy stored in our battery. And for the modeling options, we can define the temperature dependence here, and we can also define additional parameters, for example, for the aging of the batteries and the dynamic properties of the circuit, for example. So this is how easily we can go and define a new battery cell using the battery builder application. And if we want to create a parallel assembly from our battery builder, then we can create a new parallel assembly where we can define the parameters of the parallel assembly. So where we are now, we are already defining and designing the battery module where we will have 5 cells in parallel. So we can define that we want to use cell 1 that we defined previously, and we want to have 5 of those cells connected in parallel. We define some properties like intercell gaps, and we can also define the model options here. As for the cooling plate, we define a cell-based thermal resistance and a cooling plate to be at the bottom. And now we see that we are building up the module, and we are using and defining some parameters. So as for the balancing strategy, we are using passive cell balancing here. What Simscape Battery Builder offers is the following. So it offers also read-only properties where you can check the cumulative cell capacity and the cumulative cell energy of your system, for example. So here we see that we have a 14 amp hour cumulative cell capacity currently and the 140 watt hours of cell energy. So we already have our parallel assembly defined, and we want to scale it up to a module. And for this, we can create a new module by clicking on the module and start defining the building blocks of the module itself. So you see that for the parallel for the module, we are using the parallel assembly that we created previously, and we are using 6 of those parallel assemblies connected in series to create our battery module. Again, we are defining some geometrical parameters, but we are also defining the model resolution to be grouped. So we will introduce some simplification in our model, and we will use one parallel assembly as one cell in our later model. Again, for the balancing strategy, we are using passive cell balancing, and the coolant thermal path and cooling plate, we are using cell-based thermal resistance and bottom cooling plate defined. So if we want to export our module that we have built, and if we want to use it and implement it to a model, then we have 2 options. So we can either export it to a workspace variable or to a mat file. This will store the battery properties for later use, and we can open it up either from here or from the MATworks or MATLAB workspace. But if we want to create models, then we can click on the Create Library, and it will generate a library file for us in Simulink. So I have predefined the library that you can see here, and what it creates, this Create Library Export option, it gives us one library file and one library folder, for example. So for the library file, the module example, we have this format. So we have exported our module. We have the balancing port and the electrical ports and the thermal port active for it. So this is how we can build a module for our system. And now we are already on the module level, but we want to have also pack level. So as for the module, we have used the battery builder application, but I want to show you how you can use the battery builder API to scale up your module to build a detailed pack. So we state and we create a module assembly first, and you can see that we are using commands that come with the Simscape Battery toolbox, and only with those like less than 20 lines of code, we can go from a battery module to a battery pack, where we define the parameters. So the module assembly command will create a module for us, a module assembly for us that you can see here. And the command pack will create a battery pack for us. And we can also define the modeling strategy for the module and for the pack itself. And I have created the 2 variants. So you can see that here we have a detailed battery pack strategy and the lump battery pack strategy for both of the applications that we will use our batteries. So you see that the simulation strategy for the detailed pack is more high fidelity model, while for the lumped pack we have one cell representing the whole battery pack. So this is how we can go from cell to pack using the Simscape battery workflow. And now that we have our module and now that we have our battery pack designed, we can start the implementation of those. And as for the implementation, we are going to create a test module with a battery management system environment, where we will take our battery module, the 5P6S battery module, and create a plant model inside Simulink, and we will implement battery management system around it inside Simulink. So we will have a cell balancing, constant current, constant voltage charge and discharge algorithm, and a state of charge algorithm, state of charge estimation algorithm for our system. So let's take a look at this system inside Simulink. You can see that we have the battery module that we defined previously. You can just drag and drop it from your system. So you can see that I open up the module, I drag and drop it, and once you have it inside your model, those are identical. So once you have it inside your model, you can create the Simulink connections to it. And here you can define additional parameters, like for the open circuit voltage and also for cell balancing the shunt resistance, for example. But you have many options for the dynamics and thermal properties of your battery itself. So what we have here is a thermal system connected to it. So we have a cooling, an edge cooling for the bottom cooling plate, which connects to the thermal port. And we have a balancing command that connects to the balancing port. We are driving a controlled current source to the system, and we are measuring the voltage of the battery module during the simulation. As for the cell balancing algorithm, we are using the passive cell balancing block from the Simscape Battery library. And what we do is we enable cell balancing when the state of charge is higher than 80%. And the threshold that we are using for the balancing is 0.5% that we can define here. So moving on, we have constant current, constant voltage charge and discharge algorithm here, and we are using the battery CCCV block for this, again from the Simscape Battery library. So this is also an off-the-shelf block that you can use if you start to use Simscape Battery. So what we do is we control the charge and discharge using the battery CCCV block, and what we do is we start the charging when we reach 30% of the battery state of charge, and we stop the charging when we reach 90% of the state of charge of the battery module. So moving on, we have the state of charge estimation left. So in the state of charge estimation, we are using a hybrid estimation method. So we are using both a Kalman filter estimation, and we are using also a Coulomb counting estimation. So, and we are switching between those two during the simulation using this switch block here. So now we have the simulation set up. We are measuring the properties of the module itself and the battery properties using this probe block here, and it is connected to this battery module, and we are measuring the state of charge, the model current, the temperature, and also the model voltage. And what we are going to do is we will compare the state of charge from the model and of the estimated state of charge in our simulation. As for the simulation, we are running 5 hours of simulation, and we will explore the results for the simulation as well. So from here, I will not run the simulation right now, but I have prepared the simulation for you so that we can jump right into the results. So you can see on this scope here that we have the state of charge, the estimated and the actual state of charges on this plot. Right below, we have the temperatures of the module, and next to it, we have the module voltage and the module current. And we have the balancing command and the model voltage plot right on the right of the scope. So You can see that once we start the simulation, we start with a charging period, and after we reach the simulation of 3000 seconds, the temperature of the cells start to increase, and we continue to charge with constant current. And once we switch from constant current to constant voltage, the temperature of the module and the cell starts to decrease, and we continue the charging. And during the cell balancing, we have zero current. We draw no current from the battery, and we introduce no current to the battery, so we do the balancing. And once we reach the threshold of 0.5% for the state of charges, then we can start to discharge the balanced battery module. And from this time, we start to discharge, and we are applying 70 amperes of current to the battery module, and we keep discharging the battery until we reach the state of charge of 30%, and we continue charging and discharging the batteries until we reach the 5 hours of simulation time. So this is how you can use Simscape Battery to build a module and to build battery management system and thermal management system for your module itself. Moving back to the results, I would like to highlight two minor details for the state of charge estimation and cell balancing. So you can start that we started the state of charge estimation not from the same points where we had the state of charges of the battery cells. So we started a bit above. And we can see that the state of charge estimation algorithms are working perfectly because we are matching the actual state of charges of the battery cells. And also during the cell balancing, you can see that the state of charges of each cell go toward the same state of charge. And once we reach the threshold of 0.5% in state of charge, we start to draw energy from the batteries. And also on the temperature changes, we can see that we have different temperatures for different cells inside our battery module. So this phenomenon is due to the following fact. Our battery cell, we are applying cell edge cooling for the battery module, and our battery cells have different coordinates regarding the whole edge cooling, related to the whole edge cooling. So this is kind of natural that we will have a slight difference in the temperature of the cells. So this is due to the fact that we have the modeling of the different coordinates of different cells. So this is how you can get different temperature for different cells. And with this, I want to conclude the battery module implementation. And I want to show you that where we are currently. So we started with a cell design. We implemented a thermal management and a battery management system algorithm for our battery module. But what we have still left is to implement our battery pack design that we created previously into our electric vehicle system. And for this electric vehicle system, we will use an electric vehicle reference application, which is an electric car, and it represents a full electric vehicle. And it can be found in the powertrain block set. So this is a pre-built example that we will modify during our example. And this model is capable of drivetrain analysis, battery management system design and test, and control and diagnostics design, and also supports hardware in the loop simulation. You can see the architecture of the whole model on the right. So we have a battery and electrical energy transfer between the battery and the motor, and we have mechanical energy transfer between the electric motor and the rest of the drivetrain. So what we will do is we will use this model to implement our battery pack into the system, and we will replace the original battery with the battery that we have designed previously. As for the drivetrain and the battery parameters, we will use the battery pack that we designed previously. So we will have a capacity of 80 kilowatt hours. The pack voltage is around 400 volts, sorry. And the number of cells in series is 96, and the number of cells in parallel are 30. And as for the vehicle parameters, we have the vehicle mass of 1,500 kilograms, and we have a front wheel drive configuration setup. And the power and the torque that we are driving from the car is 450 Newton meters as for the torque, and the power is 210 kilowatts. And we are going to use VLTC class 3 test cycle for the battery and the whole vehicle in order to test the battery that we designed. So as for the battery, we have created two variants. We have a detailed pack and we have a lumped pack. For this simulation, as we are talking about high-level system simulation, we are going to implement the simplified and lumped battery pack into the system. So let's take a look at the model and let's jump back to Simulink. So again, I opened up the electric vehicle reference application previously, and we are using the MATLAB project for this, and we open the electric vehicle reference application using this shortcut here. So I have opened it up in advance, and you can see the same representation that you could see on the slide. So we have a passenger car in our model, we have the controllers, and here we have the drive cycle defined that we are using the VLTP class 3 cycle. Inside the passenger car, we have an electric plant subsystem where we define the battery and where we implement the battery that we have, battery pack that we have created previously. So here we have the lumped pack implemented, and you can again discover that we are using the same thermal management for the battery pack. So we are using and measuring the voltage of this whole model and the battery model, and we are driving this battery voltage further to the drivetrain itself. So this is where we have the plant model, and as for the battery management system, we have that in the controllers. So here in the controller, inside the powertrain control module, not in the control module, but in the battery management system, sorry. We have the battery management system implemented. So we have a state of charge estimation, and we have the balancing logic here, and we have an additional state machine that is controlling the whole drive cycle and controlling the whole simulation for us. So here we have the setup, and we have the parameters, and we have everything prepared. So what is left is to run the simulation. So we are running 1,800 seconds of simulation, and we can explore the results. So as we have the pack implemented, and the simulation is 1,800 seconds, it would take a while. So I have run the simulation in advance, so we can take a look at the simulation results from this scope that I prepared accordingly. So what you can see on this screen is that we have the drive cycle that we are following. So we are following this velocity profile that you can see here on the top left corner. And the rest three scopes are showing the electric parameters and properties of the battery and the electric system. You can see that we started with a state of charge of 75%, and we reached somewhat above 69% in the end of the simulation of 1,800 seconds. And you can see how the battery current is changing the simulation as we are requesting torque from the motors, And you can also see the battery voltage of the whole battery pack. So with this, you can see that we were able to implement our battery pack into an electric vehicle, and we were successful in creating a battery pack model, and implementing it in an electric car model. So I would like to summarize what we have talked about today. So in the beginning, we talked about Simscape Battery and how you can move from cell design to system implementation using Simscape Battery. We introduced thermal management and battery management system algorithms to our battery module, and we used a simplified pack design based on the battery module that we implemented in an electric car model. So with this, I wanted to show you how broad the application of Simscape batteries, and I want to thank you for your attention. And I would like to give the word back to you, Angelica. So thank you very much once again.